Welcome to WTF Science, first episode, mashed potatoes and gravity. This is going to be a bit of a science and holiday sort of mix-up, and it's going to be about Thanksgiving, because Thanksgiving becomes for Christmas, and therefore we're doing Thanksgiving first. Fight me.
Dennis?
Let's have a scrap.
About fucking time, I started to think it was never gonna come.
But this is for everybody who has gone to Thanksgiving and a relative has given them shit because they decided that they were going to get an extra plate, go back for thirds, maybe grab that extra large slice of pie. I'm gonna tell you why scientifically that is a good idea. And that's why this episode's called Mashed Potatoes and Gravity.
All right, where's that turkey?
Joey, those are my maternity pants.
No, these are my Thanksgiving pants.
So we need to talk about gravity first and foremost. Gravity is something that we all kind of understand because we're not floating into fucking space, so we have an idea that gravity pulls things to each other. So gravity is one of the forces of nature. Depending who you talk to, there are anywhere between 3 and 4, and almost new research says there might be a 5th force. I don't know. And gravity is an extremely weak force. You might be thinking, but it can hold me down instead of floating into space. Well, that's true, but gravity is really, really weak. But also, gravity's force doesn't have an endpoint. Its reach is forever. It is very weak, but infinite. Long ago, there was an individual named Isaac Newton. He came up with what we call calculus, which is a way that we can find equations and be able to use curved graphs. So there's linear graphs, which are straight, and then you have exponential graphs, which are curvy. They're thick. Is this what you want, Zoomers? Is this what you want, Gen Z?
Boomers every time they see someone on their phone. Every day we stray further from God.
So basically, a bunch of individuals couldn't figure out how to do math underneath of a graph, and they didn't understand how gravity works. And Isaac Newton, who was alone in his laboratory,
I'm a master, I discovered gravity. I drop rhymes like they're falling from an apple tree. You don't match for me, you got a bachelor's degree. I got a unit of force named after me.
theorized he died a virgin.
What'd you do with the back half of your life? You freaked out, started counting coins for the bank, and you sure didn't have no wife. Oh, you wrote a book on gravity, but you couldn't attract nobody.
He was just all about the math. Figured out gravity. We call it Newton's universal gravitational equation. That equation looks exactly like this, which is hopefully on the screen right now. Making graphics is not my forte. This looks pretty weird, especially for people who are just like, who the fuck put letters in my math? I understand. I'm going to walk you through this. So the few things that I'm going to have you do, I'm going to have you figure out your mass, and we'll go over that here in a sec. We have 4 numbers that we have to figure out here. We have the capital letter G, we have M with a little 1, which is called M sub 1, we have M sub 2, and then we have R, which is our distance. We got to talk about a few things because we had to put this shit into the metric system. Most of my audience is going to be American, so they're probably not gonna understand the metric system. I don't know why I got this southern twang in my voice.
Almost every nation on earth has fallen under the yoke of tyranny, the metric system. From Beijing to Buenos Aires, from Lusaka to London, the people of the world have been forced to measure their environment in millimeters and kilograms.
First and foremost, we need to figure out your mass. Now, mass and weight are different. If I put your ass on a scale on Earth and then put your ass on the same scale on the moon, the scale would read less on the moon than it does here. Did I cut off your arms or legs or head? No.
Come on, then. All right, we'll call it a draw.
It's just the attraction that you feel between the moon and yourself is less on the moon than it is on Earth. That's your weight. Your mass is everything that you are. Your mass will not change. Your weight will, depending on where you're at. So the astronauts that are in constant free fall around the Earth, they're weightless. I'm going to use Steve. Steve weighs 220 pounds, or when divided by 2.2, 100 kilograms. So in order to find your mass, if you only know your pounds, go ahead and take your pounds and divide that by 2.2, because 1 kilogram equals 2.2 pounds. And so once you have that, go ahead and round your number to the nearest kilogram. 90.6, go ahead and say 91, or if you had 75.2, just go ahead and say 75. It makes the math a hell of a lot easier, and I'm not looking for extreme accuracy here. If we were, we wouldn't be using this equation. Now you should have your mass. So what we're going to do is we're going to put your mass, or in my case, I'm putting Steve's mass right here in M sub 1. So now you have 3 letters and 1 number. Let's go ahead and talk about the big letter G. That's known as the gravitational constant. This is a number that has been found through experimentation and observation and using equations and then finding that they fit in all sorts of other ways. Been scientifically not proven, because you don't prove things in science. It's been scientifically checked over and over and over, and this is the gravitational constant. If you were to put a kilogram and another kilogram 1 meter apart from each other, which is a little longer than a yard for you people who don't use the metric system, they would feel that amount of force, and force is measured in newtons. And so you're probably thinking, what the is a newton? Newtons are the unit that we use for force. So the number is 6.67 times 10 to the negative 11th. So once again, if you had a kilogram and another kilogram 1 meter apart, that's how much force they would feel. And if you've never seen newtons, you don't know if that's a lot or a little bit, but yeah, it's going to be very, very tiny. This is scientific notation. It's an easy way to write small and large numbers relatively effectively. So essentially, if you really wanted to write out this number, it would be a decimal point followed by 10 zeros, then 667. That's how much force that 2 kilograms 1 meter apart feel, and that's what the gravitational constant is. It's very, very, very weak. To give you an idea, the average ant weighs 4 times 10 to the negative 5th kilograms, or 0.04 grams. They are very, very light. An ant standing on the earth is 600,000 times more force than 2 kilograms separated by a meter based on gravity. Gravity is very, very, very weak. So now we have the gravitational constant, which looks like this or like this, however you want to write it out. The gravitational constant written these 2 different ways. If you're familiar with scientific notation, you can go ahead and put 6.67 times 10 to the negative 11th because you understand how to put that into a calculator. If not, you're going to have to write out the whole damn number. I apologize. Then we have M sub 1, which is your mass, or if you don't want to do the equation yourself, you're using Steve's mass, which is 100 kilograms. We need the second mass. And usually the second mass that we use is going to be Earth because it's going to be fairly easy to do. The Earth's mass is 5.972 times 10 to the 24th kilograms, or this number. It's a very massive object comparatively to ourselves. So go ahead and put 5.972 times 10 to the 24th in the area where M sub 2 is located. So now once again, your equation should have the gravitational constant, which is the 6,7 number, your mass, and the Earth's mass. And so there should only be one letter remaining, and that is R with a little 2 above it. And that is going to be our distance. So when figuring the distance between 2 objects, we use their center of mass. We're going to say your center of mass is 1 meter above the ground. It's probably not. It's probably a little bit higher than that for some people. Probably maybe a little bit lower for other people. We're going to say 1 meter. Where is the center of mass of the Earth? Well, in the center of the Earth, which is 6,371 kilometers below the surface on average. We have 1 meter, and then we have kilometers. The fuck's a kilometer, you might be saying?
I measures 3/8 of a mile. Like, start fucking saying kilometers, because no one understands kilometers or eighths. It's the same fucking difference.
Well, a kilometer is just 1,000 meters. It's a simple conversion. The metric system is designed to be simple. In the metric system, we can say, oh, I have 1,000 meters, or 1 kilometer. What we use in the United States is, oh, I've got 5,200 some feet. That's obviously a mile. What else could it be? This is a very simple system to use. I love it. I love it so much. So we're just going to change the Earth's distance, its center of mass distance, to meters, which is simple. We just put 3 zeros at the end of it. So it goes from 6,371 kilometers to 6,371,000 meters. And then you add your center of mass, which is 1, to it. So it's 6,371,001 meters. And that is your distance. Do not forget the little 2. If you're unfamiliar with what the little 2 does, it means squared. It means multiply the number by itself. Now we're able to do this entire equation. We have all of the numbers. So if you know how to use scientific notation in your calculator, awesome. If you don't, I'm sorry. It's going to be rough. So we multiply everything on top first. We just don't even look at the bottom portion just yet. Take the 6.67 times 10 to the negative 11th times your mass or Steve's mass and times the mass of the Earth. We're going to get this number. So then we need the bottom number. So we take our distance, which is squared, and just multiply it by itself. We take 6,371,000,001 times that by itself, and we get this number. And we get this giant ass fraction. So you have the top number, which you got from all the multiplication, and you got the bottom number from the squared. And then you just divide one by the other. You divide the top by the bottom. And that's going to give you this number, 981 if you're using Steve's mass. Give or take, I kind of rounded. I took a little liberty with it. So now you see 981 for Steve's mass, or you got a different number for your mass. But are you sure that's right? And we can check. You may have seen this equation. Force equals mass times acceleration. Force, once again, measured in newtons. We have your mass, and I can tell you the acceleration on Earth. For acceleration, put 9.81. If I push you out of an airplane, on average, you're going to fall 9.81 meters per second, or basically, you're going to accelerate 9.8 meters per second. So your mass is your mass, or once again, I'm using Steve's mass, and the acceleration on Earth, due to its gravitational pull, is 9.81 meters per second squared. So in my equation, I take 100 times 9.81, and I get 981. Almost exactly the same that I got in the last equation, the Newton's universal gravitation equation. So if these two numbers are pretty similar, they don't have to be exact, but if they're pretty close, you did it right. If they're off, you might have to go back into your equation and check to make sure you did it all right. If you're at this point in the video, you obviously got it right, or you're using Steve's mass, or you're just like, fuck it, I don't know what I did wrong, I just want to watch the rest of the video and see what's going on. Okay, fair enough. We know how to calculate the force of gravity between two objects, but we're not going to use the Earth anymore. I want you to pick someone that you care about and guess their weight, because I don't know if you should call them and be like, hey, buddy, how much do you weigh? Certain people, you might get smacked. You can guess. So you get their weight, or you get their mass. So if they give you their weight in pounds, or you guess their weight in pounds, convert that to kilograms, once again by dividing it by 2.2, and you get kilograms. So it's the same numbers on top now. So you have gravity, your mass, their mass being where Earth used to be. But now the distance has changed because they aren't in the center of the Earth. At least I really fucking hope not. So you got to figure out how far away that they are. And you have to do this once again in meters. You can have someone who's in the same house as you, which is fine. To probably guess feet or yards and convert that to meters. Here's the quick conversion for that. But you can pick somebody that's not in the same city or even the same state. Hell, they could be on the opposite side of the Earth. Go ahead and you can jump on Google Maps real quick. How far away is my mom in Wyoming? I can just jump on Google real quickly, get an estimate in miles, and that's what we're going to use. So if you get an estimate in miles, what you want to do is take the number of miles and divide that by 0.6. There are about 0.6 miles per kilometer. So when you divide miles by 0.6, you get kilometers. Once again, that's not in meters, that's in kilometers. So you just add 3 zeros at the end of that. 600 miles. And so you divide 600 by 0.6, you're going to get 1,000 kilometers. Add 3 zeros at the end of that. So it goes from 1,000 kilometers to 1 million meters. You take that number and tuck it down at the bottom of the fraction. Now your equation's going to have gravity, your mass, the person whose mass you picked, and the distance they are away from you. Do the same exact thing as you did last time. Multiply everything on top, write that number down, square the bottom number, which is just the number times itself, and then write that number down, and then you'll have two numbers. You'll have the top number, which is going to be all the multiplication on top, and then you're going to have the number on the bottom, which is the squared, and then divide that, top divided by the bottom. So go ahead and do that real quick. If you're at this point, you've done it. You've got some sort of number, and it is incredibly small. Like, it's undescribably small, right? But what's cool is one little thing. It's not 0. That means that there is a force between you two. If I were to snap my fingers and everything in the universe disappeared and given enough time, you would eventually meet each other. Doesn't matter where you're at in the universe, because once again, gravity is infinite. It is extremely weak, but it's an infinite force. No matter where you go in this universe, you have a single delicate and invisible thread connecting you to every star, every planet. Everything in this universe feels your presence. Every loved one feels your presence. The universe feels you, you feel the universe. This Thanksgiving, when you go for seconds or thirds, or you get that extra large piece of pie and someone gives you some shit and they say, oh wow, really put it on the holiday way, you can tell them, hey, it's just a better way to feel the universe. And then look them straight in the eye and tell them to go fuck themselves, because it's none of their goddamn business. You've been married 3 times, Aunt Kathy. Shut the fuck up. Do not feel bad for going back to get an extra helping when it's just all the better to feel the stars with. So thank you for tuning in to the first episode of What the Fuck Science, Mashed Potatoes and Gravity. I'm going to try to do something Christmas related. I'm hoping to get this out before Thanksgiving. I've had to re-record this. This one's a little bit different, a little more compressed, if you will. If you have anything that you might want to know, feel free to drop it in the comments below. Go to my socials, follow me on those socials. Please like, subscribe, follow wherever the fuck this is at, just because, one, it helps me out, because I'd love to be a science communicator for my life. I don't know if people would be like, oh yeah, Nate, he swears a lot. Please invite him to the college functions. That'll be fun. So thanks for tuning in to the first episode of What the Fuck Science, and I will see you in episode 2.